The last speaker of today is Professor Guoliang Yu, that will talk about quantitative operator K-theory, positive scalar curvature, and filling radius.
Well, thank you very much. I would like to thank the organizers for inviting me to this wonderful event. And it's great to see so many old friends also, yeah, meeting a lot of young people. Okay, so the new result I will talk about today is joint work with several young colleagues who he's a postdoc in Texas A&M. Jimmy is another postdoc in Texas A&M. I think both of them are on the job market. One of them already got a job offer, but the other one is waiting. And then Susan. Okay, so I will begin by like a very gentle introduction to so-called quantitative operator K-theory. It's a very down-to-earth elementary theory, so should be accessible to everyone. And so if I lose you, just please raise your hand. And there are also numerous open questions. Maybe I will mention some of them. Okay, all right. So this is like, it's a theory which is more refined than the usual K-theory. Historically, it was introduced to just as a tool to compute the K-theory. But I hope to convince you it has its own merit because the problem we will study and the question we will answer will depend on the framework of the quantitative operator K-theory. So in order to formulate, to encode, like to have a more finer structure, I need like some kind of geometrical structure on a system algebra. Okay, so let me see. I start with, well, just for convenience, it's a unitos system algebra. If it does not have a unit, we can add one. But with a so-called geometrical structure. So it's a very natural structure. It's very similar to what happens in geometric group theory. You like put on like some kind of length function. And here we do something similar. But in order to make it flexible, I will not use the language of length function. You can do that. Instead, I will use the language of filtration. So this geometrical structure is like just a filtration. Okay, so it's a collection of like, let me, just to make it flexible, I'm going to, so this is just a subset. It's not even a subspace. Okay, and it satisfies the condition that, well, it's kind of filtration. And then if you multiply the two, it's kind of, okay. And if you add, I think in the past, yeah, so just to make it more flexible, I allow T plus S. Okay, so of course we don't want this to be completely degenerate. So far, I can choose this to be the empty set, right? So nothing interesting will come out of it. So I want this to be non-degenerate. I need to be a little bit careful because with the example, so like if I have A here, B here, that's going to be in A plus T plus S. I actually impose the condition, it's in the inside the unit ball. So to make the framework like flexible, and I want this like the union of all T. I think T, I'm only interested in positive T. And this with the unit ball of A to be dense in the unit ball. Of A. Okay. So let me give some examples what I'm talking about. You know, this is like without interesting example, it's kind of empty. So the first example is, this is actually quite interesting even in the commutative case. Let me start with like just continuous function on the circle, okay? So what is AT? So AT is just going to be all functions in, and whose derivative, well, let's parameterize this by the angle theta. Okay. And of course, you can generalize this to, I mean, you can generalize this to any manifold, right? By just using the differential. Okay. Yeah. I will talk about, I'm planning to talk about the connection to Allen's theory of spectral triple. Yeah, so this, yeah. And, but I just to, because for manifold, in the end, you know, things we ask might depend on Riemann geometry. To be like really down to us, we can talk about this for spaces without osmosis structure. See, this is a simplicial complex. Okay. And so instead of taking the differential, I can take some discrete derivative. So replace this, you know, you take exactly the same definition, but instead taking like, you have like a pair of points. You can impose a so-called simplicial metric, right? Put like a standard metric on each simplex, then extend it. So like for pair points whose distance is at most 1 from each other. So this is like a discrete version of derivative, okay? Then less than t. So replace at by all functions f satisfying this. Okay. All right. So it turns out even there, there's a lot we don't know. I will raise some open questions, which an answer to those questions can be very helpful to solve problems in differential geometry and topology. So even there, this is already kind of non-trivial. Okay, so now for many of us, of course, commutative system algebra is not so exciting. So I think in general, if this is non-compact, you can just take C0. Okay, so the next, of course, I can look at examples like if gamma is a discrete group, or if you wish, you can be finitely generated with like a length function. Then if you take A to be, say, the group out this algebra could be max, could be reduced, depends on what you like. And then you can choose AT to be like all the sum, so the maximum, so LG is, so let me put it this way, just the length is at most T. Okay, so that's also a natural example. The next example I will look at it, it's more like a continuous version, a space version of this. And so if you have, let's just say you have say a smooth manifold with a Riemann manifold. I think this appears in previous talks, like Xiang and also Yan. Okay, so let's look at like kernel operators on, so take the Hilbert space to be L2 of M. Look at kernel operators. Like, so we can define the so-called propagation of such an operator T, and these are like support. Okay, so it's a very intuitive concept. It's just telling us how much it's propagating, like. Okay, so the cyst algebra is like all such an operator and such that propagation is T is finite, and we take a closure of this. So this was introduced by John Low. So this is called Low algebra. Okay, so in this case, you know, if there's a natural filtration, it's just T. Okay, okay, so those are the most natural examples. You can also consider like cross product and like Allen's foliation algebra. So you can, like most of the interesting examples, we can introduce such a structure. So actually, you know, you can introduce such a structure for any cyst algebra. So it's not really artificial. Okay, so now I'm going to just explain what quantitative K-theory is. So it's essentially the same definition as a K-theory, except we want it to encode the information about the geometry or this filtration. But in order to do this, we have to allow a little bit of flexibility. Instead, well, in K-theory, we use projections, we use invertibles. Now, in order to control, like encode those geometric information, we have to make, because projections are very rigid. So we allow things which are very close to projection. So those are so-called quasi-projection. I mean, but we know K-theory is very stable. If you have a quasi-projection, and you can recover the projection. So we don't lose much. Okay. All right, so for any L, okay, so I'm going to like fix some epsilon positive. I mean, it's up to your choice, but let me just well, I think 100 is more than enough. Okay, so but and so what is like KL? Just KL. I'm too lazy to put the epsilon because we fixed that. Okay, okay. So let's say 0. So this is just like a K theory. It's it's a abelian group. So this is a definition. Oh, bigger? Okay. Yeah, of course. That's not a problem. Okay, so is this big enough? Okay, yeah. Is the abelian group. We go through the usual process of, Kruskal process. Well, let me say just generated by quasi projections. So like Q. Of course, those are in like some matrix algebra, n is allowed to be flexible. Okay, so to say it's quasi projection, we mean that, well, this theory makes sense for Banach algebra, but then we have to control the norm. So for simplicity, we focus on system algebras. Okay, so to say it's quasi projection, it means it's always up. It's very close to a projection. Okay. A. Oh yeah, you're right. Q very important here. So it's controlled by this L. Okay. And similarly, we can define K1L. Okay, so, well, instead of unitary, you can require to be like quasi-unitary. Okay, all right, so, yeah, so when I say generated, you use the same kind of equivalence relation. Yeah, so. Oh yeah, yeah, that's what I'm going to do next. Okay, so actually, so quickly I will raise some. Okay. So now, so that's a good thing about this. As soon as I introduce the definition, I can ask for question I don't know the answer to, okay? All right, so actually this is open. Just for simplicial complex, okay? So X is a simplicial complex. Okay. So what is the optimal? I'm willing to negotiate what this means. Okay, I don't really insist like really the best constant L such that I mean this is even like open when it's just compact or finite simplicial complex. Of course, things like this there is a map to the usual K theory, right? Such that this is surjective. Okay, so we don't know the answer to this. I mean, we have some estimate. Okay, so I would like to say, of course, this is a very natural question, but also this is a very crucial question in answering, like in what I'm going to do, estimate scalar curvature, or even to the Novikov conjecture. Okay, so let me tell you what we know, like what is the best constant. Okay, so this is something. So here's what we know. I'm sure this is not the best constant. Okay, so this is a result. Let me just call it the same. This is, I think, with Jiaming and okay. I think the paper is just getting. I think it's published, but the data is 2024. So, but it's you can find it online. Okay, so we know, so there exists a universal constant. Does not depend on the space. Well, let me just say A, such that K. Well, actually, I mean, of course, you don't want to. If L is greater than or equal to like A, this universal constant. Well, maybe sorry, I should not use A. That's very confusing. C and to the dimension of X. Okay. Now this by itself, well, it's kind of amusing result, but you applied this to get some basically optimal like decaying property for scalar curvature. So it was like to answer some question of Gromov. So this already has some teeth, okay? It's a very down to earth result. But if you can improve the result, you know, it would be really nice. This question is in some ways, it's implicitly, it's also related to the Novikov conjecture. And so behind it has a lot to do with like, for example, I mean, I'm using a different language, but I should mention like, for example, in Allen, and Henry, like work on Novikov almost flat bundles, and then Nigel's work with Allen, and also I think like the Higginson clonal of Nigel. It's all in spirit related to this. This is like just making it in a way more systematic. Yeah, that we can prove. Actually, this is very much related to Simon's talk, just the previous talk in terms of rigidity. You can actually, well, but the interesting thing is that, yeah, so we know it's like, it will depend on the dimension, but the only way I know is through scalar curvature. I don't know how to provide examples directly, depending on the dimension. So there's something we are missing. This is such an elementary question. Why should we use scalar curvature? I mean, it's very weird, very weird. So there's a lot about this sort of thing we don't understand. I mean, it's such a, you know, you can, yeah, talk even to an undergraduate student about this. So far, I mean, there's nothing deep. Okay, very, very down to earth. Sorry. Which projection? Bot projection, yeah, the thing is that, you have one concrete projection, right? But it could be represented in many different ways. So for example, even this, right? If you do it in the long ways, like these elements, right? Okay? And this element, if you do it directly, then if you take the derivative, then it's n, right? So, but the correct way is you have to put it like this way. So there's it depends on how you represent the K-series element. So if you represent this way, then, like for the circle, you can choose the L to be 1, essentially. Okay, so of course we know, you might be right, like bot projection might serve an example, but the only way I know is through scalar curvature. Yes.
Exactly the proof of bot periodicity by bot. It means exactly going back to the Guoliang.
Yeah. Yes. Yeah, Alan is right. So using matrices, you can get an estimate, but it depends on the dimension. I think Chris wants it to be independent on the dimension. So how do you show directly? It's not. You cannot do better. So that's an excellent question. I don't have a direct way. Yeah, but I know how to show this using the bot, but through scalar curvature. So it's a little bit weird. Okay. So let me also let me also say before I move on, because let me also say that because I was learning a very interesting lesson from Alan. Alan was advertising the use of computers, and this theory can be computerized because you see, so you don't need a space because if you can choose a big finite set with this control, with this extra control, and K-series, all the K-series information are encoded. So what I'm trying to say is this kind of K-series, you can only use it. You can like model it just using finite matrices. Not only K-series, but also K-homology can be modeled using finite matrices. Instead of talking about general theory, I want to give an example, like or spectral triple. So Alan's spectral triple. I'm just going to give one example. Okay, so the first example, okay. So of course, the generator, the spectral triple, you can use this as a spectral triple. This is a continuous model. Okay, so it's an infinite, the Hilbert space is infinite. But on the other hand, you can, instead of using this, you can use you can discretize the circle. Okay. Now, what you do is, so what is the Hilbert space? The Hilbert space is just the Hilbert space of these many points. Okay. So now the operator, which is like unitary, you just shift one position. Okay. Now, so this operator, let's call this U. This U, when you, with the multiplication operator, so you just multiply, restricted to this finitely many points. So this is going to be very small delta. But if F is you restricted in T, so I fix a T. Okay, so this is essentially what is quantitative K-homology. Okay, so this also, you see, has the advantage, it's a finite discrete model. This is true, of course, for commutative algebra in general. This is the Dirac operator for the circle. But I already have an open question here. I don't know how to realize. I know for every space, every spectral triple, you can discretize this, but I don't know how. For example, for just S2, can you like implement the spectral triple coming from the Dirac operator using like a very concrete example? So I think, yeah. Yeah, but this, no, it's exactly the, because this is how quantitative spectral triple is defined. So it includes all the K-theory information. So it's equivalent. This is equivalent to this in this framework. It's exactly equivalent. And so how are we, I mean, actually, I should say it's like, in spirit, this is very related to Alan and Surikhan and what Kati mentioned it, the tolerance relation. Yeah. So it's like, yeah. So I mean, and also there's a general open question, like for cyst algebra in general, when all spectral triple can be modeled using finite matrices, finite models. I think in Karen's talk, I asked her, whether it's quasi-diagonal, so like the quantum manifold. So she said yes. So which means this can be done for all the quantum manifold. But can you do it for the Dirac? Can you have finite models for yes? Oh, this is a tuplet. I mean, this is a tuplet on the circle. For the Sophia, I don't know how. So that's a question for you. Okay, I don't know how. This is. Yeah, but writing down a natural one, we know it can be approximated. But I would like to see something very concrete. You see, this is the idea of the difference operator. And if you do it nicely, maybe you can even define some kind of discrete scalar curvature, Oh, yeah, this.
Because when you want to make a discrete approximation, what really matters is that you're precisely the otherwise finite dimensional. And operator system is a lot more flexibility.
Yeah, this is actually, I should say, I did not formalize this, but in the work with Rufus, yeah, we kind of define it for not exactly for operating system, but for subspace of cyst algebras. Yeah, more, yeah. So it has a lot of flexibility. Actually, we used this there are people who are interested in classifications. The reason we introduced this was to prove like the universal coefficient theorem for a class of cyst algebra, what we call the finite complexity. So there's an open question there. Also, is the finite complexity equivalent to what people in classification like finite length? Oh, I forgot the exact wording. So if it is, then I think that's something the classification people are interested. Yeah. So I think one way we know how to prove, but the other way we don't. Yeah. But anyway, so there's it's very down to us, but there's a lot of open questions. But it's also it's fun to play with it. Okay, so now I'm going to come back to the connection with scalar curvature, and so this is a wonderful thing. I think for my first, so just to the young people, my first 10 years of my life, I worked by myself, but after that, I never did it. So it's just, especially working with young people, it's just such a pleasure. I mean, what I'm going to talk about, because I think one of Boo, he's a differential geometer. He keeps asking me, or he taught me about things like filling radius, or what is the connection. So, and it turns out this is just the right framework to study the questions people in differential geometry is interested. Okay, so now let me explain the concept of filling radius. Okay, so that's a concept coming from differential geometry. Okay, so let's say M is just an oriented Okay, so now of course there is we know, like in this case there is a fundamental, the fundamental class. So if the dimension is n, fundamental. Oh, let me homology class. Let's see. Okay, so we want to say if this fundamental class survives if we fatten like the manifold. Okay, so what do you mean by fattening? Of course, in order to fattening this, you have to embed it into a big space. Okay, so but there's a universal embedding. Okay, so this is like it's a universal embedding. Of M. So at a first glance, it's a kind of crazy embedding on our infinity of M. Okay, so it's like all the bounded functions on M. Okay, but there is a it's a very natural embedding. Okay, so what you do is like, okay, so how do you do this? You fix a point x0 in M, then x, you map it to like d. So this is a function. Oh, this is not bounded because M is, I think our M is not compact in general, then modular. Now this is bounded, the bounded function. And this embedding, there's a name to it, I forgot the name, but this is an isometric embedding. It's very easy to show. Okay, so now we can consider, with this universal embedding, we can consider the fattening, so NR of M. That's just all like points in L infinity of M such that to the image, let me call this, Kasai, the image in L infinity, okay, is less than R, okay? So it's a universal R neighborhood of M, or like a fattening of M. Or maybe I write it here. I think this concept was first introduced by Michel. Okay, so the so-called filling radius of M is just the smallest R such that Kasai, the fundamental class, when you put it, this will be 0 in like the homage of the R neighborhood. Okay, now if you think a little bit, this space is not even locally compact. You might be worried about what do you mean by homage, but it's just you use like singular homage or so you just use the chain. So like, which is the number of such a chain with a compact subset is finite. So it still makes sense, okay? All right, so this is a filling radius. So now, so why is this an interesting concept? So like in Simon's talk, you know, geometers, I guess we are all looking for abstraction to like existence of positive scalar curvature. So this actually provides some abstraction. So here is a conjecture. We don't know the answer yet by Michel. So if so he conjectured that there exists a constant which depends on the dimension n, depending on some number sigma positive, such that if the scalar curvature for a manifold M with dimension n is greater than or equal to sigma, then the filling radius. So if true, this provides some of M is less than or equal to C. Okay. So this like provides the motivation. Like, okay, now it turns out to answer this question, and the quantitative operate K-theory provides just the right framework to study this question. Okay, so let me first, as a proposition, as a preparation. So this is like a refinement of Jonathan Rosenberg's theorem. So, and it was, I think it's published in a special volume edited, like Perspective on Scalar Curvature, with Hall, who was previously a postdoc in Texas A&M, and okay. So if there exists a universal constant, let's call omega 0, such that if the scalar curvature of M is then the high index, I guess already mentioned in Yanni's talk. So the high index coming from the Dirac operator. Let me just, Dirac operator, it's a differential operator, so it's very local. When you take the index, you know, it's represented by like the kernel operators in the low algebra. You can make, because Dirac operator, all the differential operators, you are taking derivatives. So when you take derivative by the derivative definition, you know, you only care about what's happening around that point. So it's like the propagation should be very small. So intuitively, that's very natural. So the high index lives like in the quantitative case series for any L, so it makes sense. But the thing is that, Rosenberg's theorem says that if you have positive scalar curvature, let's say positive, then the high index is 0. But you don't know in which scale it's 0. Okay, but we actually, this more careful analysis says it's in KL of the low algebra with kernel operators, our third example. Okay, so if when the L is sufficiently large, like L, something like that, okay? This probably is not optimal. You can improve, I think, the constant, but I think that's the constant in our result, okay? So you already know in like which scale this is going to vanish. Now, how are we going to relate this to the filling radius? So we want to find an index formula which contains information about this flattened fundamental class. So that's the strategy, okay? So in general, in the for generality, we don't have an answer, but under some reasonable condition, we have an answer. So that's what I want to say next. So the theorem with Bu Jimmy and the following. So let me state the theorem, then I explain how. So instead of the dimension, so what matters is the large scale dimension. Or I should say there exists a constant. I think in his result of C, let me call this, I hesitate to use, I say C1. Oh, well, that's not very imaginative. Let me call B and D and sigma, okay. And scalar curvature of M is then the filling radius is less than or equal to, actually we know it's like A to A to D to sigma. Now, what is the A? The A, I did not use A, sorry. I think the C, now I'm using, so it's the C here. It's the C here. Okay, so we have a very precise estimation. Okay, so, sorry. Yeah, we have a precise, yeah. Okay, maybe Yeah. So let me explain what this is. Okay. So asymptotic dimension is the smallest d such that for any, well, let me say R, they exist like open cover. Actually, does not have to be open, but just psychologically. Uniformly bounded. Such that any ball with radius R, so any ball intersect. So it's like the covering dimension at most. D plus 1 members. Okay. So it's a large scale version of dimension. So, but I want to, oh, sorry, in -1 minute. Well, I promise in 1 minute, just to see how to prove this. So we just need to compute or partially compute, okay? Compute the index, the high index, D in KL of the low algebra. So I should say partially in terms of the fattening, so the fundamental class in the neighborhood, the R neighborhood, right? So for certain R, okay? Now this was done because it's this kind of K group, they are not really easy to compute. So this can be done by, so to get an optimal, to get this kind of concrete constant, this was done by like, really like Allen's non-commutative geometry paper, the pairing, the K-homology with, yeah. So we don't really use the language of cyclical cycle, but the spirit of it to do the pairing, right? And using things coming from here. Okay, so yeah, but I feel like we have a lot of room to improve, and I also, so this is my feeling. I think his conjecture is incorrect in general, but we have been trying hard to provide. We have strong beliefs that, and the optimal estimation probably come from asymptotic dimension instead of just the dimension. Yeah, but so far we have not produced the example to show that his conjecture is wrong, but we are convinced that this is the case. So yeah, well, thank you very much.